Greetings! In this video, I'd like to talk about the concept of a subset, and this came up in our reading as well. So let's suppose that A and S are both sets. Then we're going to say that A is a subset of S. Sometimes we also say A is contained in S. If every element of A is also an element of S, effectively if A is made up of things that all happen to also be in this larger set S. And the notation we use for that, I've listed here. They both are sort of stretched out C's. A is contained in S. The notation on the left with the bar underneath it that kind of reminds you of a less than or equal to sign is frequently used to mean that the set S and A actually might be the same set, and we'll talk about that when we get to set equality. But then other texts choose to just use the simpler A, C, S notation, so just the stretched out C. And depending on the convention, they may be trying to say that A is what's called a proper subset of S, meaning that A is actually only made up of less than everything that's in S. This S has something extra in it. So I will tend in this class to stick just to this simple notation and allow it to extend to both ideas. But you could see either if you're looking elsewhere. The example I want to start out with for making sense of this gives us these two sets. A being the set with elements 1, 2, 4, and 7. And S is a larger set with elements 1, 2, 3, 4, 5, 6, 7, and 8. Now I can write in this case that A is a subset of S. And I can write that because for every element in A, 1, I can also find that in S. 2 can also be found in S. 4 can also be found in S. And 7 can also be found in S. So I found every element of A in S. Often this is also stated sort of as in its negated form. There is nothing in A that isn't in S. Also, if you want to show something is not a subset, you just need to find an element not in S. And that's the example I want to provide with this next. Suppose we had a second set B, and say B was 2, 4, 6, 8, 10. Was that collection of elements. Then notice that B is not in S, and the reason is because I have an element of B. 10 is an element of B, but 10 is not an element of S, and therefore B cannot be a subset. Some portion of it is not also in S. Notice visually, to say A is a subset of S, if I were to write everything that represents A in a circle, sort of in these Venn diagrams, then for A to be a subset of S is meaning that A could be drawn entirely inside of S. B could not. B had some overlap with A and some overlap with S, but there also was this item 10 that was in neither one. So here goes 6 and 8. And there's 2 and 4, and 1 and 7, and whatever numbers I'm missing, 3 and 5. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, that's, I guess, what it would look like if you actually place the elements in their different portions. Let's now look at a second example that illustrates how big subsets could be. And by big, I mean how maximal. So suppose we have the following two sets. N is a set of all odd numbers less than 10. And M is the set 1, 3, 5, 7, 9. Now I'm going to make the assumption here that when I use the phrase number, I'm talking about counting numbers. Therefore, I would start with 1 as being the smallest. So let's think about what numbers are less than 10. Well, 1 would be less than 10 and odd. 3 would be less than 10 and odd. 5, 7, 9 is also odd and less than 10. Now I want you to notice something. I just listed out the same collection of elements as the collection that I had titled M. So N was contained in M because every element of N could be found in M. You can see that correspondence. 1 is in both, 3 is in both, 5 is in both, 7 is in both, and 9 is in both. But also, for the same reason, M is contained in N. So I could say N contained in M because all of N is in M. And I can also say M is contained in N because all of M is in N. So we notice these two sets have the same elements. Now, sameness is sometimes hard to talk about, especially if you happen to have a set that was infinite, if you just were trying to like pick each one of them and check all of them individually. And so there's a way that mathematicians figured out to get around this. So we're going to say that N equals M, and the reason is because N is a subset of M, and M is also a subset of N. So all elements of M are in N, and all elements of N are in M. And often this makes it easier to prove set equality this way. You can say, well, is there, I look at everything in my first set, and I say, are those all in the second one? And then I ask the same question the other way. If I take anything in the second set, is it also in the first one? And that becomes a more convenient way, mathematically, sort of a more logically structured way of proving that two things are equal. And this is why the consequence of this is that every set is its own subset. Every set is a subset of itself. And the reason is because that's what I'm defining set equality to mean. No matter what the set A is, it's contained in itself. And this is where that or equal to notation becomes so helpful, because it allows me to say that when I talked about a subset, I might have been talking about the set itself. Additionally, there's one other subset that every set has, and that's the empty set. The empty set is always a subset of any other set. And the reason is, if there's nothing in something, then I haven't been able to find an element of the empty set that wasn't in A, because there was nothing to look for in the first place. It's what we often call a vacuous argument, or the trivial case, because it sort of falls into place because there's nothing there. It's sort of under the same argument that we say 0 is less than 1 because it has less size than 1 does. But can you say that 0 has any size? There's my philosophy for the day, but this is just an important thing to keep in mind. And then notice one last thing. If we take a set and it's a subset of another set, then two things are always the case. The intersection of those two will be the smaller one, and the union of those two will be the bigger one. And the reason is all of A was also in S. So when I look at their overlap, it's all of A. And because of the fact that all of A was also in S, when I take A and add S to it, I might as well have just considered S, because everything in A would be double counting.